Okay, good morning or afternoon, ladies and gentlemen. For today's lesson, we're going to go a little bit more, well, I find it easier, but it can be a bit tricky for some people, putting complex numbers in polar form. So effectively what we're aiming to do is understand how to work with complex numbers in polar form. Because so far, all we've worked them in is that Cartesian form of z equals a plus bi. Thankfully, previous videos, we've been able to work out the two things required to put them in polar form, which is the modulus, so the magnitude, and the argument, which is the direction. So effectively, if we're putting a complex number in polar form, we need to know both its modulus, r, or z, and its angle, or argument, over here. Effectively, if we want to convert a complex number from Cartesian form to polar form, we have to conduct the following. So if we've got z equals x plus yi, z being our real component, y being our imaginary component, x must be equal to r cos of angle. Think about trigonometry. Y must be r sine of angle times I. Remember that imaginary component. We can then rewrite them. X plus yi becomes r cos angle plus ir sine angle. And there we can substitute cos and sine addition. Cos plus sine is written as cis, cos and sine, which you guys should already remember. So r cis of angle. This gives us effectively a complex number in trigonometric polar form. So let's dive into it. So for our first example, convert the following to polar form. If we've got z at 1 plus 2i, we need to find both its modulus and arguments. So in this case, we draw it up, and it's important to draw them as well. We find the modulus. We use Pythagoras. R equals the square root of a squared plus b squared, 1 squared plus 2 squared, root 5. And I would suggest, ladies and gents, leave them in that if possible. If it's a square number, please simplify it down. If it's not, leave it like that. To find the argument or angle, we have to use tan of angle to inverse tan of the absolute of y divided by the absolute of x. So in this case, inverse tan of 2 over 1, which is 63.435 degrees. Therefore, if we wanted to write it in polar form of r cis angle, it'd be root 5 cis 63.435 degrees. Now it comes into play. Where possible, we also want to put our angle in an exact value, because if we're doing that for the modulus, we might as well do it for the argument as well. So for this, guys, excuse me, we will have to recall two different things. The first thing is the radians form of each one of our angles. And the other one are some of our exact value triangles. I'm going to get to those in a moment. Let's go through our next one here. So, if we wanted to convert 2 take 2i into polar form, we find the modulus, which is root 8, which we can simplify into 2 root 2. By drawing it up, we know our angle is going to be negative. Our inverse tan is 4. Inverse angle, is absolute y over absolute x, 2 over 2, which is 45 degrees. Or, if you look back over those things, 45 degrees is pi over 4. However, because it's in the fourth quadrant, it has to be negative. Therefore, for our polar form, r cis angle, it'll be 2 root 2 cis negative pi on 4. Our final one here. Obviously, if we can convert to polar, we can therefore convert to Cartesian. So convert the following to Cartesian form. 2 cis negative 2 pi on 3. Well, the first thing, guys, we have to draw it up. We know it says negative. We look at where negative root 2 on 3 lies on our complex plane in our third quadrant. We substitute our values in. R in this case is equal to 2. So 2 cos, our angle. I2 sine, our angle. In this case, guys, I would personally substitute our values in. Negative 2 pi over 3 is the same as negative 120. Perfect. Substitute it in. 2 times negative a half for the cos components plus 2 times negative root 3 on 2 for the I component here. This brings us to our final form in Cartesian, negative 1 minus root 3i, because the 2's cancel out. You might be wondering where we're getting our exact values for the cos and sine from. Well, effectively, we get them by looking at the actual wavelength of cos and sine. Cos starts at 1, and a full revolution at 2 pi ends up over here. And you can see where it breaks in between. For sine, it starts at 0, snakes its way back on over. This is something I would recommend you spend a little bit of time Googling, ladies and gents, because it's a little bit easier there. And lastly, guys, with the exact value triangles, this is something that Mr. Russell has gone through, and it's something we will 100% be using for the next couple of lessons. Our first triangle, which has equal 45-degree angles. 45 degrees is the same as pi on 4. How we have this? 1 and 1 for our opposite and adjacent, root 2 for our hypotenuse. For our other exact value triangle, 1 for our opposite, root 3 for our adjacent, 2 for our hypotenuse over here, with our respective angles at pi on 3, 2 pi on 3. All right, guys, give these next questions a shot, and I'll see you in the next one.